Right.
This is
Here's
like
stroma.
yeah.
Are you taping really?
Yes, I am. That's exactly. No, really, come here. Come and look at my screen right now.
Okay. The inner membrane is, what is this thing called? It's the inner membrane that's folded up, but when it gets folded up into the disc, we give it a special name. It's called the Yes.
Wait, what
Correct.
is grammar?
The stroma is the grana is the stackum. So a grana is a stack of coins. Okay. So that's the thylakoid membrane. It's the same thing as the inner membrane, right? Inside of this is the thylakoid space, right, which is continuous with the intermembrane space. Okay. There is a second membrane that runs around out here that is the inner membrane. And this would be the intermembrane space.
Isn't the inner membrane connected to the thylakoid?
The inner membrane space is connected
But we're
to
saying that it's
the thylakoid.
It's down
So
there.
the inner
Right,
membrane space
yeah, I mean, it's-
equals the thylakoid.
All of the thylakoids are connected to each other.
So the inner membrane, like, would it just go like that and then create like a thylakoid?
Yeah,
Like,
it goes around and then it goes in and makes the thylakoids. And the thylakoids are like little discs and they're all connected by what's called lamellae.
Okay.
Okay? Alright, so in the thylakoid we have got an electron transport chain. Right? And I tend to just draw them that look like this. And then we have got ATP synthase. Okay? Here's the ATP synthase. Right? This one is which photosystem?
Two.
This one is,
One.
PS2 is which wavelength of light?
680.
680.
680.
680.
Sure.
Yeah, 100%.
680.
PS2 is going to be P680. This is going to be P700. Okay? What happens is a photon of light hits the electron transport chain, right? It excites electrons in the chlorophyll, the double bonds to the chlorophyll, they get excited, they go to a higher energy state. As they fall back down and lose energy, they pass from electron carrier to electron carrier, right? And when they do that, protons get pumped across the membrane. From out here. What does that make in here?
High concentration.
High concentration. Okay. If we've got electrons passing down the membrane, we need to replace them with some other electrons. Where do those other electrons come from?
Water.
Water. Okay, so in cellular respiration, water was the final electron acceptor. Here it is the electron donor. Water's going to come in, it's going to release oxygen, it's going to release protons, and it's going to replace the electrons that got excited with some electrons from water. Okay? The protons flow into the thylakoid space where they are trapped. They can't go anywhere, right? So they build up a high concentration. Which way do they want to go if they possibly could go somewhere?
Out.
Do we want to go out? Do they have something they can go out through?
The ATP.
ATP synthase, right? So the protons can go this way. When they do that, what do we make? ATP. Okay? So the point of photosystem 2 is to make ATP. Okay? Question?
What happens to the hydrogens?
What happens to the hydrogens that are dropped off out here? Right? They get pumped in here. They come back out here. And then we're going to need them over here. Okay, they can get pumped back in, and we also need to remove them. Okay, so what happens now is a second photon of light strikes photosystem 1, exciting electrons, and now the electrons that leave come over here to an enzyme called NADP+ reductase. And what does NADP+ reductase do?
Produces NADP.
Produces NADP+ to NADPH. What do you need to make NADPH from NADP plus?
Electrons,
Two
hydrogen.
electrons and
You need hydrogen and you need those electrons. All right, so we make NADPH, which can come down here, and we need ATP, which can come over here, okay, to the Calvin cycle. We need also to keep this concentration out here low in the stroma, right? So two things happen to keep that concentration low. One is we tie up some of them with NADP plus going to NADPH, right, which removes them, and we pump them back in here, right, which makes this high, this low, and to maintain that low concentration, because we have a constant influx of new electrons from water and new protons from water, right, we need to have something that takes them away and gets rid of them, and that's what the NADPH does, it removes them, okay? Takes it down to the Calvin cycle. Now,
what is it called when you stop making the NADPH and you do the cycle thing?
okay, so periodically, so this is non-cyclic electron flow, right? It's linear. It's going from one side to the other. Okay? The problem is we need, for ATP, we need 18 of these for every 12 of those that we need. So periodically, the NADPH comes back, turns off the little enzyme that makes this happen, and we get electrons simply cycling. Okay, so that we run photosystem 2 more often than we run photosystem 1. So we make more ATP than we do NADPH, because we need relatively more ATP than we do NADPH for the Calvin cycle.
What is that called?
That's called cyclic electron flow. Okay.
So it's called non-cyclic if both are running and cyclic if only photosystem 2 is running.
Yep. Non-cyclic and cyclic. Okay. So we go to the Calvin cycle. What have we done at this point? Have we harnessed light energy?
Yes.
Yes.
Yes. Have we converted it to chemical energy? Yes. Right? The energy from the light is now stored in ATP and NADPH. What's the problem with stopping here?
You can't store it
it
for long term.
Yeah, ATP is the cellular work, right? So if ATP is floating around, it's going to just do cellular work. We need to store it in something we can put away for a while, right? We need to be able to bank it. NADPH, right, needs to get the protons, electrons off of it so it can go back to NADP plus to keep that cycle going, right? You don't have an infinite supply of it to store, to store it up. So these are not good for storing it. So we need some way to store it more long term. That's what the Calvin cycle does. So the Calvin cycle is going to take 3 5s, 3 5-carbon things, that have a phosphate on each side.
Where did those come from?
This is a cycle, right? So they're getting regenerated. Right? So we can ask the question of where did the first one come from, but evolutionarily it doesn't. It's not just like a binary thing. Oh, geez, now something's here. So you got 3 5-carbon things. This is called RUBP. Right? There is an enzyme called rubisco. That is the done one. That's going to add 3 CO2s, which are 1 carbon apiece, to each of these 3 5-carbon things. If you take a 5-carbon thing and add a 1-carbon thing to it, you get a what?
6
6 carbon.
6-carbon thing. Yay.
Your friendly glucose.
4 carbons.
Okay, we still got phosphates on here. We don't need to know what that is called. It simply splits in half. Okay? And we end up with 6 3-carbon things, each with a phosphate. Okay? So we got 6 3-carbon things with a phosphate, but the 3-carbon thing is in the wrong shape. Okay?
Does that have a name?
That does have a name, but we're not really worried about it. We're really black boxing tons of this, right? I mean, this is like a 10-step process, and we're just skimmed over. So we need to change the shape of this into 3-carbon things that are called G3Ps. Or PGAL, if you're old school. Okay, this is 6G3P. All right. In order to make that happen, what do we need to add?
H6,
ATP and NADPH. How many things are we working on? 6 of them. So how many ATPs do we need? 6 of them, 1 per. So we need 6 ATP. And we need
6 NADH.
6 NADPH. Okay? That gives us our G3Ps. One of the G3Ps leaves. Okay? One G3P leaves. What's the difference between what? They do look the same because we're not drawing them in detail. I'm just drawing follow the bouncing carbon.
Wait, so why do you need those ATP and NADH discovered?
In order to make the rearrangement, so yes, you're sticking a phosphate on at one point, and then you're taking a phosphate off in this course of rearrangements. Okay? So, we get 6 G3Ps right over here. One of them leaves, leaving us with how many G3Ps? 5 G3Ps. 5 G3Ps at 3 carbon each is 5 times 3 total carbon. 15. We need to get back to 3 things at 5 carbons each, which is also how many carbons? 15. But in order to make this rearrangement from 5 3s to 3 5s, we're going to need a little more what?
ATP.
ATP, right? How many more ATP?
3. Making 9.
Okay, so 3 ATP. We get back, we've regenerated our RUBP, right, Navin? So that we're ready for the cycle to go again, okay?
Where does the 6th G3P
The 6th one
Yeah.
goes off over here, and when it picks up another G3P, right, this is from one Calvin cycle, we get another one from another run of the Calvin cycle, and together they make glucose. So remember the first step in cycle respiration, which was to take glucose, right, 6 carbons, and split it into G3P? We just do the reverse.
So it's 2 cranks of the Calvin cycle to get 1
2
glucose?
cranks of the Calvin cycle to get 1 glucose. Right? So this is times 2. Right? So if we run this thing twice, how many ATP are required for 1 run of the Calvin cycle?
18?
9. 2 runs? 18. In ADPH, 1 run? 6. 2 runs? 12. Product of 1 turn of the Calvin cycle, how many G3Ps? 1. 2 G3Ps from 2 turns of the Calvin cycle, and 2 G3Ps equals 1
Glucose.
Yes, ma'am.
It's alright, I don't understand why you need the 6 ATP and the 6 NADP.
We can pull out a biochem textbook and look at the arrangements that are going on. I don't think you want to do that, okay? Suffice it to say that you've got 6 molecules that you need to rearrange, and they need energy. Where do they get the energy from to be rearranged? They get the energy from ATP. So if you're working on 6 molecules, you need 6 ATPs. If you're working on 6 molecules, you need 6 NADPHs to provide you with the energy from ATPs and to provide